Right now, as you're watching this video, you are traveling through time slower than someone on the International Space Station. Not metaphorically, actually, measurably slower. The astronauts up there are aging less than you are, right this second. Their clocks are running faster. Their time is literally moving at a different speed than yours. And here's the part that will shatter everything you think you understand about reality. This isn't a malfunction of the universe. This is exactly how the universe is supposed to work. Time doesn't flow at the same rate for everyone. It never has. It never will. What if I told you that nothing in the universe can travel faster than light? Not because we haven't figured out how yet, but because going faster than light would be like traveling north of the North Pole. It's not just difficult. It's not just impossible with our current technology. It's fundamentally meaningless. The speed of light isn't the speed limit. It's the structure of reality itself. Welcome to the most mind-bending journey you'll take today. By the end of this video, you won't just understand why nothing can go faster than light. You'll understand why that limitation makes you possible, why it creates the structure of cause and effect, and why the universe would literally stop making sense without it. Before we dive into the deepest rabbit hole of physics, do me a favor. Hit that like button and subscribe, because we're about to break your brain in the best possible way. And drop a comment telling me where in the world you're watching from, and what time it is for you right now. Because by the end of this video, you'll realize that your now isn't the same as anyone else's now. Time zones are quaint little human inventions. The reality is far stranger. Let's begin. Let's start with what seems like a simple question. How fast is light? 299,792,458 meters per second. In more familiar terms, light travels fast enough to circle the Earth 7.5 times in 1 second. Fast enough to reach the moon in 1.3 seconds. Fast enough to travel from the sun to Earth in about 8 minutes and 20 seconds. But here's what will blow your mind right from the start. That number, 299,792,458 meters per second, isn't just fast. It's the fastest anything can possibly go. Not just the fastest anything has gone. Not just the fastest we can currently make things go. The fastest anything can go, period. Full stop, forever. Think of it like this. Imagine the universe is a video game, and the speed of light is the frame rate of reality itself. Just like you can't have more frames per second than the game engine allows. Nothing in our universe can move faster than light, because light speed is literally the speed at which reality updates. But why? Why this number? Why any limit at all? The story begins in 1865 with a Scottish physicist named James Clerk Maxwell. Maxwell wasn't trying to find the speed limit of the universe. He was just trying to understand electricity and magnetism. He wrote down 4 elegant equations that described how electric and magnetic fields interact with each other. These equations are so beautiful, so fundamental, that physicists still use them today exactly as Maxwell wrote them over 150 years ago. Here's where it gets interesting. When Maxwell solved his own equations, something weird popped out. The mathematics predicted that electric and magnetic fields could create waves that would propagate through empty space. And when he calculated how fast these electromagnetic waves should travel, he got a number, 299,792,458 meters per second. Maxwell realized something profound. Light was an electromagnetic wave. His equations had just explained what light actually is, but they also predicted something disturbing. According to his math, these electromagnetic waves should always travel at the same speed, regardless of how fast the source was moving or how fast the observer was moving. This made no sense. Think about it this way. If you're standing still and someone throws a ball at you at 50 miles per hour, you'll measure it going 50 miles per hour. But if you're running toward the ball at 10 miles per hour, you'll measure the ball approaching you at 60 miles per hour. If you're running away from the ball at 10 miles per hour, you'll measure it approaching at only 40 miles per hour. This is common sense. This is how velocity works for everything we experience in daily life. But Maxwell's equations said light didn't work this way. They said that if someone shines a flashlight at you, you'll measure the light traveling at 299,792,458 meters per second. And if you run toward the flashlight at 1,000,000 meters per second, you'll still measure the light traveling at exactly 299,792,458 meters per second. Not 300,792,458. Not a single meter per second faster. This seemed absurd. Physicists spent decades trying to figure out what was wrong with Maxwell's equations. Surely, there had to be some medium through which light waves traveled, like how sound waves travel through air. They called this hypothetical medium the luminiferous ether. If the ether existed, then light would only travel at 299,792,458 meters per second relative to the ether, and the problem would be solved. In 1887, two American physicists, Albert Michelson and Edward Morley, designed an experiment to detect the ether. Here's the logic. Earth is moving through space as it orbits the sun. If light travels through the ether, then as Earth moves through this ether, we should be able to detect a kind of ether wind. Light traveling in the direction of Earth's motion should be slightly slower than light, traveling perpendicular to Earth's motion, just like it's harder to swim against a current than across it. Michelson and Morley built an incredibly sensitive instrument called an interferometer that could detect tiny differences in the speed of light traveling in different directions. They ran the experiment. They checked their equipment. They ran it again. They found absolutely nothing. No difference. Light traveled at the same speed in every direction, regardless of Earth's motion. This was a crisis. The experiment had failed to find the ether, but more importantly, it had confirmed Maxwell's disturbing prediction. The speed of light really is the same for all observers, no matter how they're moving. Here's what will bend your mind. This isn't just a curious fact about light. This one observation, that the speed of light is constant for all observers, means that time and space cannot be constant. If light speed is the same for everyone, then time and space must be flexible, must stretch and compress to make the math work out. And that brings us to the most important year in physics, 1905. In 1905, Albert Einstein was a 26-year-old patent clerk in Switzerland. He had a PhD in physics, but couldn't get an academic job. So he spent his days evaluating patent applications and his nights revolutionizing our understanding of reality. Einstein looked at the Michelson-Morley result and the constancy of light speed, and instead of trying to explain it away, he asked, what if this is just true? What if the speed of light really is the same for all observers, no matter how they're moving? What would that mean for the universe? He published a paper called On the Electrodynamics of Moving Bodies. Today, we call it special relativity. And it changed everything. Here's Einstein's radical insight. If the speed of light is constant for all observers, then time and space must be relative. Different observers moving at different speeds must experience time at different rates and measure distances differently. Think of it like this. Imagine you're on a train moving at half the speed of light, and you shine a flashlight forward. From your perspective on the train, the light beam travels away from you at the speed of light, 299,792,458 meters per second. But someone standing on the platform watching the train go by also measures that same light beam traveling at 299,792,458 meters per second, not at half the speed of light plus the speed of light. How can this possibly work? How can the light be traveling at the speed of light relative to you on the train, and also the speed of light relative to someone on the platform, when you're moving at half the speed of light relative to that person? The only way this works is if time passes differently for you on the train than it does for the person on the platform. From the platform observer's perspective, your clock on the train is ticking slower. Your seconds are longer than their seconds. And the distances you measure on the train are contracted compared to what they measure on the platform. This isn't an illusion. This isn't a measurement error. Time literally runs slower for objects moving faster. Here's the equation Einstein derived. If you're moving at some velocity v, then time for you passes at a rate equal to the square root of 1v squared per c squared times the rate it passes for someone at rest, where c is the speed of light. Let's make this concrete. Imagine you get on a spaceship and travel to a star 10 light years away at 87% the speed of light. For people on Earth, this journey takes about 11.5 years. But for you on the spaceship, time is passing slower. When you arrive at the star and check your clock, only 5.7 years have passed for you. You've aged 5.7 years, while everyone on Earth has aged 11.5 years. This has been tested, not with spaceships traveling at 87% light speed, but with atomic clocks on airplanes. In 1971, physicists Joseph Haffel and Richard Keating flew atomic clocks around the world on commercial airliners. When they landed and compared these clocks to identical atomic clocks that had stayed on the ground, the flying clocks were behind by exactly the amount Einstein's equations predicted. The clocks on the airplane had experienced less time because they were moving. This happens with GPS satellites right now. GPS satellites orbit Earth at about 14,000 kilometers per hour. At that speed, time on the satellites runs about 7 microseconds per day, slower than time on Earth due to their velocity. If we didn't account for this time dilation, GPS would accumulate errors of about 10 kilometers per day. Your phone's GPS works because engineers programmed it to account for Einstein's relativity. But here's where it gets really wild. The equation I showed you, that square root of 1v squared per c squared, has a critical feature. As your velocity v approaches the speed of light c, that square root approaches 0. When time is multiplied by 0, time stops. At the speed of light, time doesn't pass at all. And if you tried to go faster than the speed of light, then v would be greater than c, and v per c squared would be greater than 1, which means you'd be taking the square root of a negative number. Time would become imaginary. Not in the colloquial sense of pretend, but in the mathematical sense of involving the square root of -1. Reality would stop making sense. Here's your first major retention hook, the question that will drive the next section. If time stops at the speed of light, and light travels at the speed of light, does that mean time doesn't pass for light itself? Does a photon experience time? The answer is going to break your brain. But first, we need to understand why nothing with mass can reach the speed of light in the first place. Let's talk about mass and energy, because this is where the speed limit of the universe becomes not just a quirk of time dilation, but a fundamental barrier written into the fabric of existence. You probably know Einstein's most famous equation, E equals mc. Energy equals mass times the speed of light squared. This equation tells us that mass and energy are interchangeable, two forms of the same fundamental stuff. But Einstein actually derived a more complete equation for objects in motion, E equals mc, where gamma is that same factor we saw before, 1 divided by the square root of 1, v squared per c squared. Here's what this means. As an object moves faster, its energy increases. But not just the kinetic energy you learned about in high school, the mv kind. At speeds close to light speed, the energy of a moving object increases according to that gamma factor. Let me make this concrete. Imagine you want to accelerate a spaceship. When the spaceship is moving slowly, adding energy makes it go faster in a straightforward way. But as the spaceship approaches light speed, something strange happens. The faster it goes, the more energy you need to add to make it go even faster. And as the velocity approaches the speed of light, the amount of energy needed to go faster approaches infinity. Think of it like this. Imagine you're pushing a shopping cart. At first, each push makes it go noticeably faster. But the closer it gets to the speed of light, the heavier the shopping cart becomes from your perspective. Not because the cart is actually gaining mass, but because the energy you're adding is contributing to what physicists call relativistic mass. By the time you've accelerated the shopping cart to 99.99%, the speed of light, it would take the energy output of a star to make it go even 0.001% faster. And to actually reach 100% light speed would require infinite energy. This has been demonstrated in particle accelerators. The Large Hadron Collider, the world's most powerful particle accelerator, accelerates protons to 99.9999991% the speed of light. At this speed, the protons have as much energy as a flying mosquito, even though a proton is trillions of times smaller than a mosquito. The LHC pumps enormous amounts of energy into these protons, but it can never quite get them to light speed. The closer they get, the more energy it takes to go faster, following that equation exactly. Here's what will blow your mind. This isn't a technological limitation. This isn't because the LHC isn't powerful enough. Even if you could harness the energy of every star in the observable universe, you still couldn't accelerate a single proton to exactly the speed of light. The universe itself forbids it. But photons, particles of light, travel at light speed. How do they do it? The answer is almost too simple. Photons have zero mass. That E equals gamma mech squared equation I showed you. If mass is zero, then it doesn't matter that gamma approaches infinity at light speed. 0 times infinity is undefined in mathematics, but in physics, it works out to mean that massless particles must travel at exactly the speed of light. Not close to it, exactly at it. Photons can't go slower than light speed, and they can't go faster. This means there are exactly two kinds of particles in the universe. Massless particles that must always travel at the speed of light, like photons and gluons, and particles with mass that can never reach the speed of light, like electrons, quarks, and everything made of them, which includes you and me and everything we've ever touched. Here's a thought experiment that might break your brain. Imagine you're a photon leaving the sun. From the perspective of someone on Earth, you take 8 minutes and 20 seconds to reach Earth. But from your perspective as a photon, because you're traveling at light speed and time doesn't pass for you, the journey is instantaneous. You're emitted from the sun and absorbed by someone's retina in the same moment of your existence. From the photon's perspective, if a photon could have a perspective, the entire journey across 150 million kilometers of space takes 0 time. Every photon that has ever existed, from the first photons in the Big Bang to the photons hitting your eyes right now, experiences the entire universe as a single timeless moment. The Big Bang and the heat death of the universe are the same instant from light's perspective. Now here's where it gets really strange. If you can't go faster than light, and light takes time to travel from one place to another, then there's a fundamental limit to how quickly information can travel through the universe. This creates something physicists call the light cone. Imagine you're at a specific point in space and time. Draw a cone upward from that point into the future, with the slope of the cone determined by the speed of light. Everything inside that cone represents events you could potentially influence, because you could send a signal or travel there at less than light speed. Everything outside that cone is causally disconnected from you. You can't influence it, and it can't influence you until enough time has passed for light to connect you. This means the universe has a structure to cause and effect. Events can only influence other events that are within their light cone. Past events caused you to be here right now. You can cause future events. But events happening right now in the Andromeda Galaxy, 2.5 million light years away, can't influence you for another 2.5 million years, and you can't influence them for the same amount of time. Here's the retention hook for this section. If nothing can go faster than light, not even information, then what does this mean for simultaneity? Can two events be happening at the same time in any meaningful sense? Or is the very concept of now an illusion? The answer is going to shatter your intuition about the present moment. Ask yourself this question: what is happening on Mars right now? Your intuition probably says, well, something is happening on Mars at this exact moment, even if I can't see it yet. Maybe a dust storm, maybe nothing dramatic. But something is definitely occurring there in the present moment, simultaneously with me asking this question. Your intuition is wrong. There is no right now on Mars. There is no universal present moment that includes both you on Earth and anything on Mars. The question, what is happening on Mars right now, is literally meaningless in physics. It's like asking, what's north of the North Pole? The question seems to make sense grammatically, but it's asking about something that doesn't exist. Here's why. Remember that the speed of light is constant for all observers, regardless of how they're moving. This seemingly innocent fact has a devastating consequence called relativity of simultaneity. Let me give you a thought experiment that Einstein himself used. Imagine you're standing on a train platform. A train goes by at half the speed of light. Exactly when the middle of the train passes you, two lightning bolts strike. One hits the front of the train and one hits the back of the train. Because you're standing at the midpoint and the lightning bolts strike simultaneously from your perspective, you see both flashes of light at the same time. You conclude that the lightning strikes happen simultaneously. But there's also someone sitting in the middle of the train. From their perspective, something different happens. Because they're moving toward the point where the front lightning bolt struck, the light from the front bolt reaches them before the light from the back bolt. But light always travels at the same speed for all observers. So if the light from the front bolt reached them first, the only explanation is that the front bolt struck first and the back bolt struck second. From their perspective, the lightning strikes were not simultaneous. Both perspectives are equally valid. There's no view from nowhere that can tell you which lightning bolt really struck first. The order of events depends on the relative motion between observers. Here's what this means. Events that are simultaneous for one observer are not simultaneous for another observer moving relative to the first. Your now includes events that another observer's now doesn't include. And their now includes events that yours doesn't include. Think about what this does to the concept of the present moment. You think there's a thin slice of time called now that includes everything happening in the universe at this instant. But relativity says there is no such slice. Someone moving past you at high speed has a different now that includes different events than your now. Someone else moving past you in a different direction has yet another now. The present moment isn't universal, it's personal. It depends on your motion through space. This gets even weirder when you think about the universe as a whole. In 1908, mathematician Hermann Minkowski, who had been Einstein's teacher, realized something profound. If space and time are relative, then we shouldn't think of them as separate things. We should think of them as different dimensions of a single four-dimensional entity that Minkowski called spacetime. In this four-dimensional spacetime, the past, present, and future all exist. They're just different regions of the geometry, like how north, south, east, and west are different directions in space. When you travel forward in time, you're not watching the present moment move on some cosmic timeline. You're moving through a four-dimensional geometry where all moments already exist. This view is called the block universe. The past isn't gone. The future isn't yet to be. Everything that has ever happened or ever will happen exists simultaneously in the four-dimensional structure of space-time. The flow of time is an illusion created by your consciousness moving through this structure. Here's what will really bake your brain. In the block universe view, you exist not as a three-dimensional object moving through time, but as a four-dimensional object stretched out through space-time, a world line connecting your birth to your death. Every moment of your life exists permanently in space-time. You're reading these words right now in one slice of space-time, but you also exist as a child in another slice and as an old person in yet another slice, assuming you live that long. The physicist Carlo Rovelli put it beautifully. We are not in time. We are time. But here's the paradox that bothered Einstein for the rest of his life. If the past, present, and future all exist equally in space-time, then what happened to free will? What happened to the open future? If your entire world line already exists in space-time, then isn't everything predetermined? Einstein never found a satisfying answer to this question. He eventually concluded that the distinction between past, present, and future is a stubbornly persistent illusion. But he never stopped being bothered by what this meant for human experience. Now, some physicists reject the block universe interpretation. They argue that while relativity of simultaneity is real, it doesn't necessarily mean the future already exists. The mathematics of relativity doesn't require that interpretation. But here's the thing. Even if you reject the block universe, you still have to accept relativity of simultaneity. You still have to accept that there's no universal now. Here's your attention hook. If there's no universal present moment, if simultaneity is relative, then what does this mean for causality? If two events happen and different observers disagree about which happened first, doesn't that break the whole concept of cause and effect? The answer involves something called the light cone structure of spacetime, and it's going to save physics from descending into complete chaos. Let me ask you a disturbing question. If different observers can disagree about which of two events happened first, then couldn't they also disagree about which event caused which? If Alice sees event A happen before event B, and Bob sees event B happen before event A, then from Alice's perspective A caused B, but from Bob's perspective B caused A. Wouldn't this destroy the entire concept of cause and effect? Wouldn't the universe become a contradictory mess where causes come after effects and nothing makes sense? Here's where the cosmic speed limit saves us. The speed of light doesn't just limit how fast things can go. It creates a structure in spacetime that preserves causality. Remember the light cone I mentioned earlier? Let's go deeper into what it actually means. Imagine you're at a point in spacetime. You can draw two cones from that point, one extending into the future and one extending into the past. The slope of these cones is determined by the speed of light. The future light cone contains all events that you could potentially influence by sending a signal at or below light speed. The past light cone contains all events that could have influenced you by sending a signal at or below light speed. Everything else, all events outside both light cones, is causally disconnected from you at this moment. These events are in a region that physicists call elsewhere. Here's the beautiful, mind-bending part. Events in the elsewhere region are the only events where different observers can disagree about time order. If event A is inside your past light cone, then every observer in the universe, regardless of their motion, will agree that A happened before now. If event B is in your future light cone, every observer will agree it happens after now. The only events that observers can disagree about are events that are causally disconnected from you, events that couldn't have influenced you and that you couldn't influence. In other words, the relativity of simultaneity only applies to events that couldn't interact with each other anyway. Events that can actually cause each other have a definite time order that all observers agree on. This is why the cosmic speed limit preserves causality. If you could send signals faster than light, you could send signals outside your light cone. And if you could do that, different observers would disagree about which signal was sent first and which was received first. You could create situations where, from some observer's perspective, the reply to a message arrives before the message was sent. In fact, it's even worse than that. If faster-than-light communication were possible, you could send yourself messages into your own past. Let me show you how with a thought experiment. Imagine you and a friend are moving apart from each other at high speed. You send your friend a faster-than-light message. From your perspective, The message arrives at your friend in the present moment or near future. But from your friend's perspective, because of relativity of simultaneity, the message arrived in their past. Now your friend sends you a faster-than-light message back. From their perspective, they're sending it to your present or near future. But from your perspective, because you're moving relative to them, their reply arrives in your past, potentially before you sent your original message. You've just sent yourself a message into your own past. You've created a closed causal loop, a violation of causality where effects precede causes. This is why physicists are so confident that faster-than-light travel is impossible. It's not just that we haven't figured out how to do it. It's that allowing faster-than-light travel would break causality. It would allow time travel to the past with all the paradoxes that entails. Think about what this means. The speed of light is the speed of causality. It's the maximum speed at which cause and effect can propagate through the universe. When physicists say, nothing can go faster than light, what they really mean is nothing can go faster than causality. Here's something that will blow your mind. This applies to gravity too. Einstein's general theory of relativity, published in 1915, describes gravity not as a force, but as a curvature of spacetime caused by mass and energy. When a massive object moves, it creates ripples in spacetime called gravitational waves. These waves travel at exactly the speed of light. This means if the sun suddenly vanished right now, Earth wouldn't immediately fly off in a straight line. Earth would continue orbiting for 8 minutes and 20 seconds until the gravitational wave from the sun's disappearance reached us at exactly the same moment that the last light from the sun reached us. The speed of light is also the speed of gravity. In 2015, physicists detected gravitational waves for the first time using the LIGO experiment. These waves came from two black holes colliding 1.3 billion light years away. The researchers measured the speed of these gravitational waves. Want to guess what they found? The waves traveled at the speed of light to within a tiny margin of measurement error. But wait, there's something even weirder we need to talk about. I said nothing can go faster than light, but there's a caveat that's going to seem like a cheat code in the universe. While nothing can move through space faster than light, space itself can expand faster than light. Here's a question that sounds like a riddle. If nothing can go faster than light, how can there be galaxies so far away that we can never see them, even if we wait forever? The answer is going to introduce you to one of the most bizarre features of our universe. Space itself can expand faster than light, and in fact, most of the universe is expanding away from us faster than light speed right now. Let me be very clear about what this means and doesn't mean. Objects cannot move through space faster than light. That's still forbidden. But space itself can expand, carrying objects along with it, and this expansion can happen faster than light. Think of it like this. Imagine you have a rubber sheet with two ants on it. If an ant crawls across the rubber sheet, it can't go faster than ant running speed. But if you stretch the rubber sheet itself, you can separate the ants faster than they could possibly run, even if neither ant is actually moving relative to the rubber beneath its feet. This is exactly what's happening in the universe. Space is expanding, and distant galaxies are being carried away from us by this expansion. The farther away a galaxy is, the more space there is between us and it, and the faster the expansion carries it away from us. In 1929, astronomer Edwin Hubble discovered this expansion by measuring the light from distant galaxies. He found that galaxies farther away were moving away from us faster than nearby galaxies. And the relationship was perfectly linear. A galaxy twice as far away was moving away twice as fast. This relationship is now called Hubble's law. Here's where it gets wild. If you extrapolate Hubble's law far enough, you reach a distance where the expansion of space is carrying galaxies away from us at exactly the speed of light. This distance is called the Hubble radius, and it's about 14.4 billion light years away. Galaxies beyond this radius are receding from us faster than light. Light from these galaxies can never reach us, not now, not ever. These galaxies are outside our observable universe, not because light hasn't had time to reach us yet, but because the expansion of space is carrying them away faster than their light can travel toward us. It's like trying to swim against a current that's flowing faster than you can swim. And here's the truly unsettling part. Because the expansion of the universe is accelerating, more and more galaxies are crossing the Hubble radius every day. They're disappearing beyond the edge of the observable universe, and they will never be visible again. In the far future, trillions of years from now, beings living in galaxies that remain gravitationally bound to each other will look out at the sky and see only their local group of galaxies. They'll have no way of knowing that billions of other galaxies even exist, because all evidence of them will have been carried away beyond the light speed barrier. But wait, doesn't this violate relativity? Didn't we just establish that nothing can go faster than light? Here's the subtle but crucial point. Special relativity, the theory Einstein published in 1905, only applies to objects moving through space in a fixed spacetime. It doesn't apply when spacetime itself is changing. When Einstein developed general relativity in 1915, he discovered that mass and energy curve spacetime, and that spacetime can be dynamic, expanding, or contracting. In general relativity, the speed of light is still a local speed limit. No object can overtake a light beam in its immediate vicinity. If you were somehow riding along with a galaxy that's receding from us faster than light, you would still measure any light beam passing you as traveling at exactly 299,792,458 meters per second. You wouldn't notice anything strange locally. The faster-than-light recession happens because of the accumulation of expansion across the vast distance between us and that galaxy. It's like if you're on a super long conveyor belt. Each section of the belt is moving at a normal speed, but the combined effect of all those sections moving can carry you along faster than the speed limit for moving on the belt. This leads to something absolutely mind-bending. There are galaxies we can see now whose current location is beyond the Hubble radius. We're seeing light that left them billions of years ago when they were closer to us and receding slower than light. But by the time we're seeing that ancient light, the galaxy itself has been carried so far away by expansion that it's now receding faster than light. Here's another way the universe seems to break the light speed barrier: quantum entanglement. When two particles are entangled, measuring one particle instantly affects the other, no matter how far apart they are. If you have two entangled electrons, and you measure the spin of one electron and find it spinning up, you instantly know the other electron is spinning down, even if it's on the other side of the galaxy. Einstein hated this. He called it spooky action at a distance, and argued it couldn't be real because it seemed to violate the cosmic speed limit. If measuring one particle instantly affects another particle light years away, isn't information traveling faster than light? But here's the trick. You can't actually use entanglement to send information faster than light. When you measure the first particle, you get a random result. The correlation with the distant particle is perfect, but it's a correlation between random results. You can't control the outcome of your measurement, so you can't encode a message in it. To know that your particle's result is correlated with the distant particle's result, you need to use normal light speed or slower communication to compare notes. Quantum entanglement is real. Physicists John Clauser, Aling Aspect, and Anton Zeilinger won the 2022 Nobel Prize in Physics for experiments proving this beyond any doubt. But it doesn't violate causality because it doesn't allow faster-than-light information transfer. The universe has this beautiful consistency. Every time it seems like the light speed limit might be violated, there's a subtle reason why it isn't. The limit holds absolutely for anything that could carry information or energy from one place to another. Space can expand faster than light, but that's space itself, not objects moving through space. Quantum correlations can be instantaneous, but they can't transmit information. Here's your retention hook. If the speed of light is so fundamental, if it's really the structure of causality itself, then where does this speed limit come from? Why is light speed the value it is? Could it have been different? The answer is going to take us to the deepest level of physics, to the structure of spacetime itself. Let's address the question that might have been nagging at you. Why is the speed of light 299,792,458 meters per second? Why not 1,000,000 meters per second? Why not infinite? Here's something that will blow your mind. That number is actually arbitrary. It's an artifact of the units we chose to measure distance and time. The meter was originally defined as 1/10,000,000th of the distance from the equator to the North Pole. The second was originally defined based on the rotation of the Earth. These are fundamentally human choices. In fact, as of 2019, the meter is now officially defined in terms of the speed of light. 1 meter is the distance light travels in 1/299th, 792,458 of a second. We've literally baked the speed of light into our definition of distance. What's not arbitrary is that there is a cosmic speed limit and that it's finite. But why? Why is there a maximum speed at all? To understand this, we need to think about the geometry of spacetime. In the 3 dimensions of space, we learn Euclidean geometry. The distance between 2 points is given by the Pythagorean theorem. Distance squared equals x squared plus y squared plus z squared. But spacetime isn't Euclidean. It has a weird geometry, first described mathematically by Minkowski. In spacetime, the distance between 2 events, called the spacetime interval, is given by spacetime interval squared equals time difference squared, spatial distance squared. Notice that minus sign. That minus sign is everything. It's what makes space-time fundamentally different from ordinary space. It's what creates the structure of past, present, and future. And it's what creates the cosmic speed limit. That minus sign means that as you move faster through space, you move slower through time in such a way that your total speed through space-time remains constant. Everything in the universe is always moving through space-time at exactly the speed of light. When you're sitting still in space, all your motion is through time. When you move through space, some of your motion through time gets converted to motion through space. Think of it like this. Imagine space-time is a 4-dimensional highway, and every object has a velocity vector in this 4-dimensional space. The length of this vector is always c, the speed of light. When the vector points entirely in the time direction, the object is at rest in space and moving through time at the maximum rate. When the vector tilts toward the spatial directions, the object moves through space, but the time component must decrease to keep the total length at c. Massless particles like photons have their velocity vector pointing entirely in spatial directions, with no time component. That's why time doesn't pass for photons. That's why they must travel at the speed of light. This geometric view reveals something profound. The speed of light isn't really about light at all. It's about the geometry of space-time. Light just happens to travel at this fundamental speed because photons are massless. If we lived in a universe without light, the cosmic speed limit would still exist. Physicists sometimes call it c, not for light in English, but for celeritas, Latin for swiftness, to emphasize that it's a fundamental constant of spacetime, not specifically about light. But here's the deeper question. Why does spacetime have this geometry? Why the minus sign in the spacetime interval? Could spacetime have a different structure? The honest answer is, we don't know. As far as we can tell, this is just a fundamental feature of the universe we inhabit. It's part of the initial conditions of reality. Some physicists speculate that there might be a deeper theory, perhaps involving quantum gravity or string theory, that explains why spacetime has the structure it does. But right now, we can only observe the structure and work out its consequences. However, we can ask, what would a universe with a different speed limit be like? If the speed of light were slower, the universe would be very different. Time dilation and length contraction would become noticeable at lower speeds. If light speed were, say, 100 kilometers per hour, then driving a car would cause measurable time dilation. Twins going on road trips in different directions would age at different rates. But there's something more fundamental. The strength of chemical bonds, the stability of atoms, the rates of nuclear reactions, all of these depend on the fine structure constant, which involves the speed of light. If you changed the speed of light, you would change the fine structure constant, and you would likely make atoms unstable. Stars might not be able to form. Life would almost certainly be impossible. If the speed of light were infinite, meaning there was no cosmic speed limit, then cause and effect could propagate instantaneously. There would be a universal present moment. But, and this is crucial, there would also be no way to reconcile electromagnetism with relativity. Maxwell's equations wouldn't work. Electromagnetic radiation wouldn't exist. Light wouldn't exist. The universe seems finely tuned so that the speed of light is just right to allow the complex structures we see, including ourselves. Here's something that might break your brain one more time. In quantum mechanics, there's a relationship between energy and frequency called Planck's relation. E equals hf, where h is Planck's constant and f is frequency. And there's a relationship between momentum and wavelength. P equals h lambda. These relationships, combined with special relativity, lead to the conclusion that particles can be described as waves and be described as particles. The speed of light shows up in the relationship between energy and momentum for all particles. E equals pc squared plus mc squared. For massless particles, this reduces to E equals pc, which means they must travel at speed c. For massive particles, there's an extra term that prevents them from reaching speed c. The speed of light is woven into quantum mechanics, into general relativity, into electromagnetism, into every fundamental theory of physics we have. It's not just a random fact about the universe. It's a structural feature of reality itself. And here's the most mind-bending implication. If the speed of light is the speed of causality, and causality is what allows one moment to lead to the next, then the speed of light is the speed at which time flows. It's the rate at which the future becomes the present, and the present becomes the past. You're moving through time right now at the speed of light, just pointed in the time direction rather than a spatial direction. We've spent over an hour diving into the physics of light speed, relativity, and the structure of space-time. But now I want to bring this back to you, sitting here watching this video. Because this isn't just abstract physics. This is literally the structure of your reality. Right now, at this very moment, you are traveling through space-time at the speed of light. Not metaphorically, literally. Your world line through four-dimensional space-time has a length, and you traverse that length at exactly c, the cosmic speed limit. The reason you experience time passing is because you're moving through the time dimension of space-time. When you move through space, you're redirecting some of your motion from the time dimension to spatial dimensions, which is why time slows down for moving objects. But your total speed through space-time never changes. Let me make this personal. Every decision you make about how to move through space is simultaneously a decision about how you move through time. When you get on an airplane and fly across the country, you age slightly less than someone who stays on the ground. The difference is tiny. We're talking nanoseconds, but it's real. You've borrowed a tiny bit of time from the future by moving through space. If you could somehow board a spaceship and travel to a distant star at 99.999% the speed of light, you could journey for subjective months or years while centuries pass on Earth. You would arrive in Earth's distant future, having barely aged. You can't travel backward in time, but you can absolutely travel forward faster than the normal rate by moving through space at high speed. This isn't science fiction. This is the structure of reality. The only reason we don't experience it in daily life is that our speeds are so low compared to light speed that the effects are minuscule. But here's what really matters. The cosmic speed limit isn't a limitation on your freedom. It's what makes your freedom possible. Think about it. If there were no speed limit on causality, if effects could propagate infinitely fast, then everything would be connected to everything else instantaneously. Any action anywhere in the universe would immediately affect every other point in the universe. There would be no way to isolate a system, no way to have local causes produce local effects. The universe would be an incomprehensible tangle of instant correlations. The cosmic speed limit creates space and time as distinct things. It creates the possibility of local physics, where you can understand what's happening near you without needing to know the state of the entire universe. It creates the possibility of autonomy, where your choices can have local consequences that propagate outward at a finite speed. The light cone structure of spacetime means you have a sphere of influence that grows at the speed of light. Every decision you make, every action you take, creates ripples in causality that spread outward. Right now, your past actions have influenced events within your past light cone. Your future actions will influence events within your future light cone. But beyond those cones, you are causally disconnected. You are free from those events, and they are free from you. This is what free will looks like in physics. Not some kind of supernatural ability to violate cause and effect, but the fact that causality has structure, and within that structure, there's room for you to make choices whose effects propagate forward in time. Here's another personal implication. When you look at the night sky, you're looking backward in time. The light from the sun is 8 minutes old. Light from the nearest star, Proxima Centauri, is 4.2 years old. Light from the Andromeda Galaxy is 2.5 million years old. The most distant galaxies we can see sent their light over 13 billion years ago, when the universe was young and the Earth didn't exist. You can never see the universe as it is. You can only see the universe as it was. The cosmic speed limit means the present moment of distant objects is forever hidden from you. You can see their past, and in the future, you'll see what is their present now, but you can never see what they're doing right now, because right now doesn't mean the same thing for you and them. This means, in a very real sense, the night sky is a time machine. Every photon that enters your eye has traveled for years, centuries, or eons, and carries information about the conditions where and when it was emitted. When you look at the Andromeda Galaxy, you're seeing what it looked like 2.5 million years ago, before humans evolved on Earth. If aliens on a planet in Andromeda are looking at Earth right now with a powerful telescope, they're seeing Earth as it was 2.5 million years ago, before humans. They would see a planet with early hominids, with no cities, no technology, no sign of modern civilization. This has a profound philosophical implication. There is no universal now that you can appeal to. Number God's eye view of the universe as it exists at a single moment. Reality is fundamentally local and relativistic. Your experience of the present moment is yours alone. And yet, despite the seeming isolation, you're connected to the universe through causality. Light from distant stars reaches your eyes. The atoms in your body were forged in stars that exploded billions of years ago. You are literally made of stardust, connected through vast chains of causation to the Big Bang itself. The cosmic speed limit doesn't isolate you. It connects you to everything else through a structured web of causes and effects, a web that extends across space and time, linking every moment to every other moment that could possibly influence it or be influenced by it. Now let's talk about faster-than-light travel, because this is where science fiction and actual science diverge in fascinating ways. Every science fiction franchise has some version of faster-than-light travel. Star Wars has hyperspace. Star Trek has warp drive. Dune has the Holtzman drive. These are narrative necessities because space is so vast that at light speed, it would take years to reach the nearest stars and millions of years to cross the galaxy. Stories need to compress these timescales. But here's what most science fiction gets wrong. Faster-than-light travel isn't just really difficult. It doesn't just require enormous amounts of energy. It's fundamentally incompatible with causality. Let me show you why with a concrete example. Imagine faster-than-light travel is possible, and you have a spaceship that can travel at twice the speed of light. You want to send a message to a star 10 light-years away. You accelerate your message to twice light speed, and from your reference frame, it arrives at the star in 5 years. Great. But remember relativity of simultaneity. Different observers have different definitions of now. For an observer moving at high speed relative to you, events that are simultaneous for you are not simultaneous for them. If your FTL message is traveling outside the light cone, different observers will disagree about when it was sent and when it was received. For some observers, your message arrives before it was sent. Not just from their perspective, actually arrives in an objectively earlier time. And if that recipient can also send FTL messages, they could send a reply back that arrives before your original message was sent. You've created a closed time-like curve. You've sent information into your own past. This opens up all the classic time travel paradoxes. You could send yourself a message telling you not to send the original message, creating a logical contradiction. You could learn information from your future self. But where did that information originally come from? These aren't just plot holes in movies. These are genuine logical impossibilities that break the structure of cause and effect. Some science fiction tries to get around this with wormholes or warp drives that bend space-time rather than moving through it faster than light. These are clever ideas, and they're not necessarily ruled out by physics. General relativity does allow solutions that include wormhole shortcuts through space-time that connect distant regions. The problem is that all the wormhole solutions physicists have found require something called exotic matter with negative energy density. We've never observed exotic matter, and there are good reasons to think it might not exist. Even if it does exist, the amounts needed to hold a human-sized wormhole open would likely require more negative energy than exists in the observable universe. Warp drives have similar issues. In 1994, physicist Miguel Alcubierre proposed a theoretical warp drive that contracts space in front of a ship and expands space behind it, allowing the ship to effectively move faster than light without locally exceeding the speed of light. But Alcubierre's solution also requires exotic matter with negative energy density, and calculations suggest that the energy requirements are astronomical, possibly more than the mass energy of the entire observable universe. Even if you could create a warp bubble, there's another problem. You couldn't control it from inside. To turn the warp drive on, you'd need to send a signal to the front edge of the bubble, but the bubble moves faster than light, so your signal can't reach the front edge. You'd need to set up the warp bubble before getting inside it. And how do you set it up in the first place? Every proposed faster-than-light travel method runs into one of these issues. Either it requires impossible amounts of exotic energy, or it creates causality violations, or it can't be controlled, or some combination of these problems. But here's something interesting. While you can't travel faster than light, you could potentially travel very close to the speed of light. If you could build a spaceship that accelerates at 1 gram, Earth's surface gravity, continuously, you could reach the center of the galaxy in about 20 years of ship time, even though the galaxy is 26,000 light-years away. How? Time dilation. While 20 years pass for you, over 26,000 years would pass on Earth. From your perspective on the ship, the galaxy would be length contracted, so you'd have less distance to travel. From Earth's perspective, you're moving at 99.999% of light speed, and your clock is running incredibly slowly. Both perspectives are valid. Both give the same final result. This means that, in principle, you could travel across the entire observable universe in a single human lifetime, at least from your perspective. The catch is that when you arrived, billions of years would have passed on Earth. Everyone you knew would be dead. Civilizations would have risen and fallen. The sun might have burned out. You'd be traveling not just across space, but into the deep future. This is the only kind of time travel that relativity allows. Forward in time by moving through space at high speed. You can't return. You can't bring back information. But you can skip forward through the centuries. Here's what this means. The cosmic speed limit doesn't make space exploration impossible. It makes it one way. It makes it a journey, not just to new worlds, but to new times. So far, we've talked about light speed in the context of relativity. But there's another fundamental theory of physics, quantum mechanics. And quantum mechanics has its own strange relationship with the cosmic speed limit. In quantum mechanics, particles don't have definite positions and velocities until you measure them. Before measurement, they exist in superpositions, being in multiple places or having multiple velocities simultaneously. This sounds like it might conflict with relativity. If a particle doesn't have a definite position, how can we talk about how fast it's moving? The answer is that quantum field theory, the synthesis of quantum mechanics and special relativity, describes particles as excitations and fields that fill all of space. The electron isn't a little ball moving through space. It's a ripple in the electron field. Photons are ripples in the electromagnetic field. And here's where it gets interesting. These fields obey relativity. Information in the field can only propagate at or below the speed of light. When you create a particle here, the disturbance in the field spreads outward at the speed of light, carrying the information that a particle was created. This leads to some deeply weird consequences. In quantum field theory, the vacuum of empty space isn't actually empty. It's filled with quantum fields fluctuating randomly, constantly creating and annihilating virtual particles. These virtual particles can't travel faster than light either, but they can exist briefly before disappearing, borrowing energy from the vacuum in a way that Heisenberg's uncertainty principle allows. The cosmic speed limit even shows up in the uncertainty principle. Heisenberg said you can't simultaneously know a particle's position and momentum with perfect precision. The more precisely you know where a particle is, the less precisely you know how fast it's moving. But if you confine a particle to a very small region of space, the uncertainty in its momentum becomes very large. If you confine it enough, the uncertainty in momentum becomes so large that the particle could have momentum corresponding to speeds greater than light. Does this violate relativity? No, because that momentum isn't a definite value until you measure it. And when you measure it, you'll always find a value consistent with relativity. The uncertainty represents our lack of knowledge, not the particle actually moving faster than light. There's something even stranger. In quantum field theory, particles can take paths through spacetime that locally violate the cosmic speed limit, as long as these violations happen over such short distances and times that they're hidden by the uncertainty principle. Imagine a particle traveling from point A to point B. Classically, it takes a definite path at less than light speed. But in quantum mechanics, the particle takes all possible paths simultaneously, including paths that go faster than light. These faster-than-light paths contribute to the particle's quantum amplitude, affecting the probability of where you'll find the particle. However, when you sum up all the possible paths, the faster-than-light paths mostly cancel out due to quantum interference. The only paths that survive the cancellation are the ones that respect the cosmic speed limit. So even though individual quantum paths can violate the speed limit, the measurable behavior of particles obeys it. This might sound like cheating, like quantum mechanics is skirting around the rules, but it's not. The cosmic speed limit is fundamentally about what can be measured, what can carry information, what can create causal connections. And quantum mechanics, for all its weirdness, respects those constraints absolutely. Here's where it gets philosophically interesting. In quantum mechanics, the future isn't deterministic. Even if you know the exact quantum state of a system, you can only predict probabilities for future measurements. The outcome of any individual measurement is random. This randomness doesn't violate the cosmic speed limit because the randomness can't be controlled. You can't use quantum randomness to send information faster than light. The outcomes are truly random, not determined by any hidden faster-than-light signal. This is why quantum entanglement doesn't allow faster-than-light communication, even though the correlation between entangled particles is instantaneous. The correlation is between random outcomes, and randomness can't carry information. But here's something that will bend your mind. The randomness in quantum mechanics might not be truly random. There are interpretations of quantum mechanics, like the many worlds interpretation, where every possible outcome actually occurs in a branching tree of parallel universes. In this view, when you measure a quantum system and get a random result, you're not causing randomness to happen. You're finding out which branch of the multiverse you're on. If many worlds is correct, then the cosmic speed limit still holds in each individual branch, but there might be a sense in which information exists across all branches simultaneously. Some physicists have speculated that there might be ways to exploit this for computation, or even communication, but these ideas are highly speculative and might be fundamentally impossible. What we can say for certain is that every experiment ever performed, every observation ever made, respects the cosmic speed limit. Quantum mechanics is weird, but it's not so weird that it breaks causality. We've covered the basics and even some advanced concepts, but there are a few edge cases where the cosmic speed limit becomes truly bizarre. Let's explore the strangest corners of physics. First, the Alcubierre warp drive I mentioned earlier. Let me go deeper into why it's problematic. Even if you could create a warp bubble with exotic matter, there's something called the horizon problem. Once you're inside a moving warp bubble, you can't send signals to the front edge of the bubble because it's moving away from you faster than light. You're causally disconnected from your own ship's controls. You can't steer. You can't stop. You're trapped inside a runaway bubble with no way to interact with the outside universe. Some physicists have proposed modifications to the Alcubierre drive that might solve this, but they all require even more exotic matter and even more energy. The more you try to make warp drives work, the more problems pop up. Second, Hawking radiation and black holes. Stephen Hawking discovered in 1974 that black holes aren't actually black. They emit radiation due to quantum effects near the event horizon. This radiation has a temperature inversely proportional to the black hole's mass. Here's the weird part. Hawking radiation appears to come from just outside the event horizon, where quantum fluctuations create particle-antiparticle pairs. One particle falls into the black hole while the other escapes. The escaping particle is the Hawking radiation. And this is crucial, the Hawking radiation can never carry information out of the black hole faster than light. The radiation is thermal, essentially random, encoding no information about what fell into the black hole. Information might be preserved in subtle correlations in the radiation, but these correlations can only be decoded using information that must travel at or below light speed. The cosmic speed limit holds even at the edge of black holes, even in the most extreme gravity in the universe. Third, the expansion of the universe and cosmic inflation. In the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion called inflation. Space expanded faster than light, much faster. In a tiny fraction of a second, a region smaller than an atom expanded to larger than the observable universe. This sounds like it violates the cosmic speed limit, but remember, space itself can expand faster than light. What can't exceed light speed is objects moving through space. During inflation, every point in space was essentially at rest in the local space around it, but the space between points was expanding so rapidly that distant points were receding from each other faster than light. This has a bizarre consequence. There are regions of the universe that were once close enough to exchange light, but are now so far apart due to expansion that light from one can never reach the other. They're causally disconnected by the expansion of space. The universe we can observe, the observable universe, is just one causally connected region. Beyond our observable universe, there might be infinitely more space, filled with galaxies and stars, and perhaps even civilizations that we can never see and can never interact with because the expansion of space has carried them beyond our light cone. Fourth, tachyons. In the 1960s, physicists played with the mathematics of special relativity and asked, what if we solve Einstein's equations for v greater than c? What if we plug in a speed faster than light? The math doesn't break. You get solutions, but they're weird. These hypothetical particles, called tachyons, would have imaginary mass involving the square root of -1. They would speed up as they lost energy and slow down as they gained energy. And they could only exist traveling faster than light. They couldn't slow down to light speed or below. Do tachyons exist? Almost certainly not. We've never detected one, and there are good theoretical reasons to think they can't exist. If they did exist, they would allow faster than light communication and causality violation. The universe seems to forbid them, not by making them difficult to create, but by making them fundamentally incompatible with the structure of reality. Fifth, dimensional shortcuts. In higher dimensional theories, like string theory, our three-dimensional space might be embedded in a higher dimensional space. If so, there might be shortcuts through the extra dimensions, allowing you to travel between 2 points in three-dimensional space by taking a path through the fourth or fifth dimension. That's shorter than any path through our 3 dimensions. This wouldn't technically violate the cosmic speed limit because you're not traveling faster than light. You're taking a shorter path. It's like the difference between walking around a mountain versus tunneling through it. The problem is that we have no evidence these extra dimensions exist in a form that would allow this. If extra dimensions exist, they're either microscopic and curled up, or they're inaccessible to ordinary matter. We might live in a 3-dimensional brain embedded in higher dimensions, but unable to leave that brain. Still, it's a theoretical possibility that doesn't directly violate relativity. It's the closest thing to a legal loophole in the cosmic speed limit. Let's get concrete. How do we actually know that the cosmic speed limit is real? What experiments have tested it? First and most directly, particle accelerators. The Large Hadron Collider accelerates protons to 99.91% the speed of light. At this speed, each proton has as much kinetic energy as a flying mosquito, even though a mosquito is trillions of times more massive. Where does this energy go if not into increasing the speed? It goes into the relativistic mass of the protons. The faster a particle moves, the harder it becomes to accelerate it further. The LHC pumps enormous amounts of energy into protons, but they asymptotically approach light speed without ever reaching it. The behavior matches Einstein's equations perfectly. Physicists have accelerated electrons to even closer to light speed, 99.99999999988%. At this speed, time dilation is enormous. From the electron's perspective, distances are contracted by a factor of millions. But the electron still hasn't reached light speed, and it never will. Second, cosmic rays. These are high-energy particles from space that constantly bombard Earth. Some cosmic rays have energies millions of times higher than anything the LHC can produce. The most energetic cosmic ray ever detected, called the Oh My God particle, was a proton with an energy of about 48 joules roughly, the energy of a baseball thrown at 90 miles per hour, concentrated in a single subatomic particle. Even with this enormous energy, the particle was traveling at 99.99999999999999999999999% the speed of light. Not at light speed. Close, but not quite. The cosmic speed limit held. Third, supernova neutrinos. In 1987, a star exploded in the Large Magellanic Cloud, a nearby dwarf galaxy. We call it supernova 1987A, About 3 hours before the light from the explosion reached Earth, a burst of neutrinos arrived, detected by neutrino observatories in Japan, Russia, and the United States. Neutrinos are nearly massless particles that barely interact with matter. They traveled the 168,000 light-years from the supernova to Earth at very close to the speed of light. The light from the supernova arrived 3 hours later, but that's not because light travels slower. It's because the light was produced deep inside the collapsing star and took time to fight its way out through the dense stellar material, while the neutrinos passed through almost unimpeded. By comparing the arrival times and knowing when the supernova occurred, physicists determined that neutrinos travel at the speed of light to within a tiny fraction of a percent. This is consistent with neutrinos having a very small mass, making them slower than light, but only barely, or possibly being massless like photons, making them travel exactly at light speed. Fourth, the Global Positioning System. GPS satellites orbit at about 20,000 kilometers altitude, moving at about 14,000 kilometers per hour. At this speed, time dilation slows their clocks by about 7 microseconds per day. But there's another effect. At 20,000 kilometers altitude, gravity is weaker, and general relativity predicts that clocks run faster in weaker gravity. This effect speeds up the satellite clocks by about 45 microseconds per day. The net effect is that satellite clocks run about 38 microseconds per day faster than clocks on Earth. This might seem tiny, but light travels about 30 centimeters per nanosecond, so 38 microseconds corresponds to about 11 kilometers. If GPS didn't account for relativity, your GPS position would drift by 11 kilometers every day. The fact that GPS works is a constant, real-world test of both special and general relativity. Fifth, time dilation in muons. Muons are particles created when cosmic rays hit the upper atmosphere. We've covered the physics, but now let's grapple with what the cosmic speed limit means philosophically. Because this isn't just about what can or can't travel fast. It's about the nature of reality itself. First implication: the universe has a structure. Reality isn't arbitrary. There are rules, mathematical rules, that govern how things can behave. And these rules aren't just descriptions of what usually happens. They're absolute constraints on what can happen. This is profound. It means nature isn't infinitely flexible. There are some things that simply can't exist, not because we haven't figured out how to make them, but because they're logically incompatible with the structure of space-time. Second implication: the future is genuinely open. This might seem contradictory after I talked about the block universe, but hear me out. Even if all moments exist equally in space-time, the light cone structure means that causes must precede effects. The future light cone grows out of the present moment, constrained by what's physically possible. In a universe without a cosmic speed limit, without light cones, causality would be a tangled mess. Everything would influence everything else instantaneously. There would be no way to separate cause from effect. The cosmic speed limit creates the arrow of time, the distinction between past and future, the possibility of making choices that have consequences. Third implication: we are fundamentally limited in what we can know about the universe. There is a horizon beyond which we cannot see, not now and not ever, not just because light hasn't had time to reach us, but because the expansion of space carries some regions away from us faster than light. This is a cosmic humility. The universe is larger and perhaps more complex than we can ever observe. There might be regions with different laws of physics, different fundamental constants that we can never study because they're forever beyond our light cone. Fourth implication: the present moment is personal, not universal. Your now is different from everyone else's now. This doesn't mean reality is subjective or arbitrary. It means reality is richer and more subtle than our intuitive notions of absolute time suggest. This has implications for consciousness and identity. If there's no universal present moment, then consciousness can't be a global property of the universe. It must be local, tied to specific world lines through space-time. You experience time flowing because you're moving along your world line, not because time is objectively flowing for everyone. Fifth implication, reality is relational. There's no view from nowhere, no God's eye perspective that sees everything as it really is. All observations, all measurements are made from a specific perspective, a specific reference frame, and different reference frames are equally valid. This philosophical view, called relationalism, says that properties like velocity, simultaneity, and even time itself aren't intrinsic to objects, but are relationships between objects and observers. Sixth implication, the universe is comprehensible through mathematics. The fact that we can write down equations that describe the cosmic speed limit, that predict time dilation and length contraction, that account for every observation we make, is itself profound. Why should the universe follow mathematical rules at all? Why should these rules be discoverable by creatures like us, made of atoms, with brains that evolved to hunt and gather on the African savanna? Eugene Wigner, a Nobel Prize-winning physicist, called this the unreasonable effectiveness of mathematics in the natural sciences. The cosmic speed limit is part of this unreasonable effectiveness. We can write it down, understand it, use it to make predictions, and have those predictions confirmed to extraordinary precision. Seventh implication, we are part of the universe, not separate from it. The cosmic speed limit applies to you, to your thoughts, to the electrical signals in your brain. You are made of particles that obey relativity. Your consciousness exists within space-time, subject to its constraints. This means there's no cosmic exemption for human beings. We aren't observers outside the system, looking in. We're participants, embedded in the same space-time as everything else, subject to the same laws. But this doesn't diminish us. It elevates us. We are the universe becoming aware of itself. We are space-time that has organized itself into a configuration capable of understanding space-time. The atoms in your body have been on a 13.8 billion year journey from the Big Bang to right now, and that journey has resulted in you, capable of pondering the cosmic speed limit. Eighth implication, the cosmic speed limit makes meaning possible. In a universe without causal structure, without the distinction between past and future, there could be no narrative, no development, no progress. Things wouldn't happen for reasons. They would just happen in a timeless, causeless jumble. The cosmic speed limit creates the structure that allows stories to exist, including your story. Your life has a beginning, a middle, and an end, precisely because causality flows forward at a finite speed. You can make choices that matter because those choices have consequences that propagate forward in time through your future light cone. This is empowering. You aren't powerless. Within your light cone, within the sphere of causality that expands outward from you at the speed of light, you can make a difference. Your actions matter. They ripple outward, affecting the future in ways large and small. We've covered an enormous amount of ground, but the truth is, there's still so much we don't understand about the cosmic speed limit and its implications. Let me share some of the deepest unsolved questions in physics. First, why is the speed of light the value it is? We've established that the number is arbitrary, dependent on our choice of units. But why does the universe have a finite speed limit at all? Why not infinite? Is there a deeper theory that explains the geometry of space-time and predicts the existence of a cosmic speed limit? String theory and loop quantum gravity are attempts to answer this, but neither has made testable predictions yet. We're still groping in the dark for a theory of quantum gravity that might explain why space-time has the structure it does. Second, what happens at the Big Bang? Our equations break down at the moment of the Big Bang itself. Time and space seem to emerge from what? Nothing? Something? A quantum fluctuation? A previous universe? The cosmic speed limit creates a horizon that prevents us from seeing earlier than about 380,000 years after the Big Bang, when the universe became transparent to light. Before that, the universe was opaque, a hot plasma that absorbed and re-emitted photons constantly. We can never directly observe the Big Bang with light, but we might be able to observe it with gravitational waves, which would have propagated freely even in the early opaque universe. Future gravitational wave detectors might let us see back to within a fraction of a second after the Big Bang, testing our theories of cosmic inflation in the earliest moments of time. Third, is there a multiverse? Some interpretations of quantum mechanics and some versions of cosmic inflation predict that our observable universe is just one of infinitely many universes, each with potentially different laws of physics and different values for the fundamental constants. If the multiverse exists, does each universe have its own cosmic speed limit? Could there be universes where the speed limit is different, or where there is no speed limit at all? And if so, could those universes support life? Or is our value of the cosmic speed limit somehow special and necessary for complexity to exist? We might never be able to answer these questions because, by definition, other universes are beyond our light cone, causally disconnected from us forever. Fourth, does the cosmic speed limit apply to consciousness? We know it applies to physical signals, electrical impulses, chemical transmissions, everything that happens in the brain. But some philosophers and physicists have speculated that consciousness might have non-physical aspects that don't obey the light speed limit. Most physicists are skeptical of this. All evidence suggests consciousness is a physical process, emergent from the complex interactions of neurons, which are physical objects subject to relativity. But we still don't fully understand consciousness, so we can't completely rule out exotic possibilities. Fifth, can we exploit quantum entanglement for communication? I've explained why conventional quantum entanglement doesn't allow faster-than-light communication. But physicists continue to explore subtle aspects of quantum mechanics that might enable new technologies. Quantum teleportation is real. We can transfer quantum states from one particle to another using entanglement, but it still requires a classical light speed or slower signal to complete the teleportation. No information travels faster than light. Will we ever find a clever way around this limitation? Almost certainly not. Every attempt to use quantum mechanics to communicate faster than light runs into the same fundamental barrier. Quantum randomness can't be controlled, and the correlations require classical communication to verify. Sixth, what is dark energy? We know the expansion of the universe is accelerating, driven by something called dark energy. Dark energy makes up about 68% of the total energy content of the universe, but we don't know what it is. Dark energy doesn't violate the cosmic speed limit. The expansion it drives is an expansion of space itself, not motion through space. But the properties of dark energy might give us clues about the fundamental structure of space-time and the origin of the cosmic speed limit. Seventh, are there particles that travel at exactly light speed besides photons? We know photons and gluons are massless and must travel at light speed. Gravitons, the hypothetical particles that carry gravity, should also be massless and travel at light speed, but we've never detected individual gravitons. Are there other massless particles we haven't discovered yet? Some theories predict additional massless particles. Finding them would test our understanding of what it means to travel at the cosmic speed limit. Eighth, what happens to information that falls into a black hole? This is the black hole information paradox. When something falls past the event horizon, it seems like the information about its quantum state is lost forever, because nothing can escape from inside the horizon, not even light. But quantum mechanics says information can't be destroyed. So where does the information go? Hawking suggested it's encoded in subtle correlations in the Hawking radiation, but we don't understand the mechanism. This paradox has been called the deepest problem in theoretical physics. The resolution might involve quantum gravity, the synthesis of general relativity and quantum mechanics that we don't yet have. And it will certainly involve careful thinking about how the cosmic speed limit applies at the boundary between our universe and the interior of a black hole. Ninth, is the cosmic speed limit truly absolute? Or are there exceptions we haven't discovered? Every test confirms the speed limit, but science is always open to new evidence. If we found a particle that traveled faster than light, or a phenomenon that communicated information faster than light, it would overturn a century of physics. Most physicists would bet heavily against this. The cosmic speed limit is too deeply woven into too many confirmed theories. But science must remain open to the possibility of being wrong. That's what makes it science rather than dogma. Let's bring this back down to Earth one more time. The cosmic speed limit seems like it's about exotic physics, black holes, and particle accelerators. But it affects your everyday life in ways you might not realize. First, electricity. When you flip a light switch, the light turns on almost instantly, but not quite instantly. The electrical signal travels down the wire at a significant fraction of light speed, typically about 50 to 99% of C, depending on the type of wire. For the short distances in your house, this happens so fast you can't perceive the delay. But for long-distance electrical transmission, the delay is real and must be accounted for. High-frequency traders in the stock market have invested millions of dollars in faster communication lines because even a millisecond advantage can be profitable. Some have even lobbied to build straighter cable routes between cities to reduce the distance signals must travel, shaving microseconds off transmission times. This is humans competing within the constraints of the cosmic speed limit. No matter how much money you spend, you can't make your stock trades execute faster than the speed of light allows for the distance involved. Second, GPS and navigation. I mentioned earlier that GPS accounts for relativity. But there's another light speed issue. GPS works by triangulating signals from multiple satellites. Each satellite sends a signal containing a timestamp. Your GPS receiver compares the timestamps to calculate how far away each satellite is and uses geometry to determine your position. But those signals take time to travel from the satellites to your receiver, about 0.067 seconds from the satellite's altitude. Your GPS device must account for this delay. If it didn't, if it assumed signals traveled instantaneously, your position would be wrong by about 20,000 kilometers, the distance the signals actually traveled. Every time you use GPS, you're relying on engineers who understand the cosmic speed limit and have programmed your device to account for the finite speed of light. Third, the internet. When you load a web page, request a video, or send a message, the signal travels through fiber optic cables at close to light speed. For nearby servers, the delay is imperceptible. But for servers on the other side of the world, there's a noticeable lag. The minimum possible latency between New York and Sydney is about 80 milliseconds, limited by the straight line distance through the Earth, which signals can't travel through, and the actual cable paths around the Earth. No amount of technology can reduce this below the light speed limit. This is why online gaming has regional servers. If you're playing a fast-paced game from New York against someone in Sydney, the minimum possible delay in your interactions is 160 milliseconds round-trip, 80 milliseconds for your action to reach them, 80 milliseconds for their response to reach you. This might not seem like much, but in competitive gaming, it's an eternity. Fourth, astronomy and space exploration. When NASA sends commands to the Mars rovers, there's a delay between sending the command and the rover executing it. Mars is between 4 and 24 light minutes away, depending on where Earth and Mars are in their orbits. Commands take that long to arrive, and confirmation takes the same time to return. This is why Mars rovers must be partially autonomous. They can't be controlled in real time from Earth like a remote control car. The cosmic speed limit makes this impossible. Engineers must send high-level commands and let the rover figure out the details. For more distant spacecraft, the delays are even longer. The Voyager 1 probe, the most distant human-made object, is over 22 light-hours away. It takes 22 hours for a signal to reach it, and 22 hours for a response to return. Communication requires patience on cosmic scales. Fifth, speed cameras and radar guns. Police radar guns work by sending out radio waves and measuring how long they take to bounce back from your car. Radio waves travel at light speed. The gun measures the Doppler shift in the returned waves to calculate your speed. The cosmic speed limit is literally how we enforce traffic speed limits. Sixth, camera flashes and photography. When you take a photo with a flash, the light from the flash must travel to the subject, bounce off, and return to the camera sensor. This happens at light speed. For close subjects, the delay is imperceptible. But for very fast photography, like capturing bullets in flight, the finite speed of light must be accounted for. High-speed photography sometimes uses laser triggers that detect when an object breaks a beam of light. The object's motion through the beam, the travel time of the signal, and the delay in the camera shutter all happen at scales where the speed of light matters. Seventh, your perception. When you see something, you're seeing light that left that object and traveled to your eyes. You're not seeing the object as it is now. You're seeing it as it was when the light left it. For nearby objects, this delay is tiny nanoseconds. Your brain can't distinguish such short times, but it means that everything you see is technically the past, not the present. You live in a bubble of delayed information, where everything you perceive happened slightly before you perceive it. For distant objects like stars, the delay is years. You're seeing ancient light, viewing the universe's past. When you look at the night sky, you're looking at a time machine, seeing different objects at different moments in their history. Eighth, communications satellites. Satellites in geostationary orbit, used for TV and communications, orbit at about 36,000 kilometers altitude. Signals take about 0.12 seconds to travel from ground to satellite and back. This is why satellite phone calls sometimes have a noticeable delay. You're literally waiting for radio waves to travel up to space and back. Modern communications increasingly use fiber optic cables on the ocean floor instead of satellites, precisely because the light speed delay is shorter through cables across the surface of the Earth than up to orbit and back. The cosmic speed limit shapes modern technology. It's not just abstract physics. It's a practical constraint that engineers must work within every day. As we look to the future, how will humanity adapt to the cosmic speed limit? What does a future civilization look like when constrained by the speed of light? If we become a spacefaring species, spreading to other star systems, we'll face the challenge of communication across light years. A message from Earth to a colony on a planet orbiting Proxima Centauri, the nearest star, would take 4.2 years to arrive. The reply would take another 4.2 years. A simple conversation would span nearly a decade. This means interstellar civilization won't be unified in the way nations on Earth are. There can be no interstellar government with real-time control over its colonies. By the time a message arrives saying, "We have a crisis," the crisis will be 4.2 years in the past. It will already be resolved or have destroyed the colony. Interstellar colonies will necessarily be autonomous. They'll have local governments, local decision-making, local culture that evolves independently of Earth. Over centuries, colonies might diverge so much culturally and even biologically through genetic drift or deliberate modification that they become separate species or civilizations. The cosmic speed limit will create a fragmented human civilization, islands of humanity separated by vast gulfs of space and time, united only by a common origin and the slow exchange of information and culture at light speed. Some futurists imagine beanstalks of civilization, chains of colonies separated by years or decades of travel time, with culture and information flowing down the chain at light speed or slower. A new idea emerging on Earth might take centuries to reach colonies dozens of light years away. We might develop new social structures adapted to this reality. Perhaps a system where colonies are founded with a cultural package that's expected to last for centuries without updates. Or perhaps we'll develop extremely long-term planning, thinking in terms of generations and centuries rather than years and decades. Some scientists have proposed using relativistic time dilation for long-distance space travel. If you could accelerate a ship to 99.999% of light speed, travelers could reach distant stars in subjective years, while centuries pass on Earth. You couldn't return. Home everyone you knew would be long dead, but you could colonize distant worlds. This would create a strange dynamic. Earth sending out time-shifted colonists who arrive in Earth's distant future. The colonies they establish would be contemporaneous with a much older Earth civilization. Would they even still be compatible with their home culture? Another possibility, generation ships. Instead of trying to travel faster than light, we build enormous spacecraft that travel at a small fraction of light speed, with entire ecosystems and communities aboard. The people who arrive at the destination are descendants of those who left generations later. This accepts the cosmic speed limit and works within it. It makes interstellar travel a civilizational project, not an individual journey. We might also develop new forms of communication. Instead of trying to have real-time conversations across light years, we might create time capsule messages, rich packages of information, art, science, and culture sent to other colonies as gifts to be opened years later. Imagine receiving a message from Earth containing the entire cultural output of the past decade: music, movies, scientific papers, personal stories from millions of people. Not as a conversation, but as a snapshot of a moment in time, preserved and transmitted across the stars. Or we might upload human consciousness to digital form and transmit it as data. If consciousness can be reduced to information, a big if, then you could email yourself to another star system, being reconstructed from the transmitted data. You wouldn't travel faster than light. The data would take years to arrive, but you'd experience no subjective time during the transmission. This is highly speculative. We don't know if consciousness can be copied or uploaded, but if it can, it might be the only practical way to travel to distant stars while remaining yourself. The cosmic speed limit might also protect us. The distances between stars are so vast that hostile alien civilizations would have extreme difficulty attacking us. Even if they developed technology far beyond ours, they couldn't strike Earth without a years-long journey that we'd likely detect long before they arrived. The speed limit creates a form of cosmic defense through distance. Aggressive civilizations can't spread quickly. They're limited to expanding at below light speed, giving other civilizations time to detect them and respond. On the other hand, the cosmic speed limit might be part of why we haven't detected alien civilizations yet. If intelligent life is common in the galaxy, but the speed limit prevents easy interstellar travel, then civilizations might stay near their home stars, creating technological civilizations that are detectable only within a small bubble of light years. We might live in a galaxy full of civilizations, all of them isolated by the cosmic speed limit, all of them alone in their local stellar neighborhoods, watching the distant stars and wondering if anyone else is out there. The Fermi paradox, where is everybody, might be answered simply: they're there, but too far away to visit, and perhaps too different to communicate with even if we could detect their signals. In the far future, if we survive and spread throughout the galaxy, humanity might become a meta-civilization, a network of cultures connected by light-speed communication, sharing a common heritage, but evolving independently, creating a diversity of human experience that no single planet or star system could ever contain. The cosmic speed limit isn't a prison. It's a structure that shapes the possibilities for civilization. It constrains us, yes, but constraints often lead to creativity. The greatest art comes from working within limitations. The greatest civilizations might come from working within the cosmic speed limit. We're approaching the end of this journey, and I want to step back and ask the biggest question. What does all of this mean? Not for physics, not for technology, but for you, for your life, for what it means to exist as a conscious being in a universe with a cosmic speed limit. First, it means you exist in a universe that's comprehensible. The cosmic speed limit isn't an arbitrary rule handed down by fiat. It's a necessary consequence of the geometry of space-time, and we can understand this geometry. We can write equations, make predictions, test them, and find that reality conforms to our mathematics. This is miraculous. We are tiny creatures on a small planet, yet we can understand the fundamental structure of the universe. Your brain, 3 pounds of neurons running on about 20 watts of power, can comprehend ideas about relativity, about the nature of time and space, about the cosmic speed limit. You are the universe understanding itself. The atoms in your brain are the same atoms that were forged in stars, and now those atoms have organized themselves into a structure capable of contemplating the cosmic speed limit. The universe has become self-aware through you. Second, it means you have a place in the causal structure of reality. Your world line through space-time connects to past world lines that influenced you and to future world lines that you'll influence. You're not disconnected from the universe. You're embedded in it, part of the vast web of cause and effect. Every choice you make sends ripples forward in time through your light cone. You can't influence the entire universe. Most of it is outside your light cone, causally disconnected from you. But within your sphere of influence, you matter. Your actions have consequences. You are genuinely part of the story of the universe. Third, it means your experience of time is real, even if it's not universal. Yes, relativity says there's no universal present moment. Yes, the block universe interpretation suggests all moments exist equally. But your consciousness, your subjective experience of moving through time, is a real feature of the universe. You're not an illusion. You're a process, a pattern in space-time, a world line of consciousness, experiencing itself as it extends from past to future. The fact that different observers have different definitions of now doesn't invalidate your experience of now. It makes it personal, local, yours. Fourth, it means the future is genuinely open. The cosmic speed limit creates a boundary between what's determined by the past and what's not yet fixed. Events within your past light cone have already happened and can influence you. Events within your future light cone haven't happened yet and can be influenced by you. Events in the elsewhere region are causally disconnected. They can't influence you, and you can't influence them at this moment. This creates room for choice, for agency, for free will within the constraints of physical law. You're not a passive observer watching a predetermined script. You're an active participant in a universe where causality flows forward at a finite speed, creating the possibility for genuine novelty. Fifth, it means you're connected to everything else in the observable universe through light. Every photon that enters your eyes has traveled from somewhere else, carrying information about distant places and times. You're in constant contact with the stars, receiving their ancient light. And you emit light too, infrared radiation from your warm body, reflecting visible light from your surface. Photons are leaving you constantly, carrying information about you out into the universe at the speed of light. In a very real sense, you're announcing your presence to the cosmos, sending out a wave of information that will propagate forever at light speed. Sixth, it means you're part of a special moment in cosmic history. Right now, about 13.8 billion years after the Big Bang, the universe is in a phase where galaxies are visible, where stars are burning, where complex structures can exist and evolve. This won't last forever. In the far future, trillions of years from now, the universe will be cold, dark, and empty. The expansion of space will have carried all but the nearest galaxies beyond the cosmic horizon. Stars will have burned out. Black holes will have evaporated. The universe will approach a state of maximum entropy, where nothing much can happen anymore. You exist during the universe's creative phase, the era when complexity is possible, when life and consciousness can exist. You're here during the cosmic moment when the universe can look at itself and understand what it is. Seventh, it means you're mortal, but your influence is eternal. You can't live forever. The second law of thermodynamics and the structure of biochemistry guarantee that. But the effects you have on the world propagate forward in your future light cone at the speed of light, spreading outward forever. Every act of kindness, every piece of knowledge you create or share, every person you touch, these effects ripple forward. They influence other people, who influence others in an endless cascade of causation. You can't see most of these effects. They're too distant, too diluted by time, but they're real. In a universe where causality is structured by the cosmic speed limit, your life creates a permanent pattern in space-time. You are a brief, bright spark, but the light from that spark travels outward forever. Eighth, it means you should feel wonder. The universe is strange, beautiful, and comprehensible. The cosmic speed limit is just one aspect of this, but it's a profound one. It shapes the structure of reality, the nature of time, the possibility of causation, the limits of communication, the future of civilization. You are living in a universe where light has a maximum speed, where nothing can outrun its own light cone, where time is relative and space is curved, and causality flows forward at 299,792,458 meters per second. This is your reality. This is the universe you get to explore and experience and understand. Be amazed by this. Be grateful for this. You exist during a brief window of cosmic time when consciousness is possible, in a universe with a structure elegant enough to be comprehensible, yet complex enough to be interesting. The cosmic speed limit isn't a limitation on your importance. It's part of what makes your existence possible. It creates the structure of time, the distinction between past and future, the possibility of causes and effects, the space for you to make choices and have those choices matter. You are a pattern in space-time, a brief eddy in the flow of causality, a moment of consciousness in the vast cosmos. But you're not insignificant. You're the universe becoming aware of itself, if only for a moment. You're part of the greatest story ever told, the story of how the cosmos evolved, from the Big Bang to right now. To you, reading these words, understanding something about the cosmic speed limit, as we come to the end of this journey through light speed and the limits that break our brains, I want to leave you with one final thought. The cosmic speed limit is both a constraint and an invitation. It's a constraint because it limits what we can do. We can't travel faster than light. We can't communicate instantaneously across vast distances. We can't escape the flow of time by jumping outside causality. We're bound by the structure of space-time, by the geometry that says nothing can outrun light. But it's an invitation because it creates a universe worth exploring. If there were no cosmic speed limit, if causality could flow infinitely fast, the universe would be a very different place. It might not have the rich structure we see. It might not support the complexity that allows life and consciousness to exist. The cosmic speed limit creates distance, which creates diversity. If every part of the universe could influence every other part instantly, everything would quickly converge to uniformity. The speed limit allows different regions to evolve independently, creating the variety we see in galaxies, stars, planets, and life. It creates time, which creates narrative. Your life has a story because causality flows forward at a finite speed. Events happen in sequence. Causes precede effects. This ordering creates the possibility of meaning, of growth, of change, of learning. It creates isolation, which creates value. If you could be everywhere at once, nowhere would be special. If you could know everything instantly, nothing would be surprising. The cosmic speed limit ensures that knowledge must be earned through observation and exploration. It makes discovery possible. Consider what humanity has accomplished, despite or because of the cosmic speed limit. We've sent probes to the edge of the solar system, waiting hours for signals to return. We've built telescopes that let us see billions of light years into space and time. We've developed physics that lets us understand the universe on scales from the quantum to the cosmic. We've done all this as creatures who can't naturally survive in space, who live for a few decades at most, who are confined to moving far slower than light. We're working within incredible constraints. And yet we've learned so much. What might we accomplish in the future, still bound by the cosmic speed limit, but creative within that constraint? We might develop new propulsion systems that reach significant fractions of light speed. We might build generation ships that carry human civilization to other stars. We might upload consciousness and transmit ourselves as data across the void. Or we might discover that staying home, developing a deep civilization on Earth and in our solar system, is more meaningful than spreading thinly across the galaxy. We might find that working within limits, creating richness and complexity in a bounded space, is more valuable than endless expansion. The cosmic speed limit will shape these choices. But it won't prevent us from having a future worth living, a civilization worth building, discoveries worth making. Here's what I want you to take away from this video. The universe is strange and wonderful. Physics is stranger than fiction. The cosmic speed limit, this simple fact that nothing can outrun light, has implications that cascade through every aspect of reality, from the smallest particles to the largest galaxies, from the structure of time to the future of civilization. You live in a relativistic universe. Time is not absolute. Space is not absolute. Simultaneity is not absolute. The only absolute is the cosmic speed limit, the speed of causality, the rate at which the future becomes the present. And you, right now, are moving through space-time at this fundamental speed. You're always traveling at the speed of light. It's just that your motion is usually almost entirely in the time direction, with only a tiny component in spatial directions. When you walk across a room, you're redirecting some of your light speed motion from time to space. When you sit still, all your motion is through time, but your total speed through space-time, your movement along your world line, is always exactly c. You are a light speed being, existing in four-dimensional space-time, experiencing a slice of that space-time as the flowing present moment, connected to all of reality through the web of causality that extends at light speed. This is not a metaphor. This is not poetry. This is physics. This is what you are. Before I let you go, I want to ask you one more time. Hit that subscribe button if you haven't already. Share this video with someone who loves learning about the universe. Drop a comment telling me what concept blew your mind the most, or what question you still have. And remember, you're not just watching a video about the cosmic speed limit, you're experiencing it. The light from your screen is traveling at c, hitting your retinas, being converted to neural signals that propagate through your brain at a significant fraction of c, creating the thoughts and understanding that you're experiencing right now. You are physics in action. You are the universe understanding itself. The cosmic speed limit isn't something external to you. It's part of the fundamental structure of your existence. Thank you for taking this journey with me. Thank you for caring enough about the universe to spend hours learning about light speed and relativity and the nature of time. That curiosity, that desire to understand, is one of the most beautiful features of human consciousness. Keep asking questions. Keep learning. Keep being amazed by this strange, wonderful, comprehensible universe we get to inhabit. The cosmic speed limit is real. Time is relative. The future is open. And you matter. Now go out there and live in a relativistic universe. Make choices. Influence your future light cone. Be part of the story of the cosmos. Thank you for watching. I'll see you in the next video.